All right, well, hope you're doing well. And like I said, we'll eventually find out about the election. We'll see. I didn't like the idea that some states allowed till not this Friday, but even next Friday. That if it has a postmark by yesterday, they're thinking it might take that long to somehow get the mail in. That seems weird to me. But anyway, that's the way it is. Now, they won't always do that. If they know that there's one person has, let's say, 100,000 lead, and there's only 10,000 outstanding ballots, then they can declare that. Okay, even if you want all 10,000, it wouldn't be enough. So that's why they can do that. All right. All right. So the first part of the quiz would have to do with instrumentation, kind of like what you were doing last week, and some of the questions might have to do with when you measure, do you always use sig figs? And when you did your lab, I know that in most cases you did use sig figs, but the most obvious one where I saw you didn't, and I tried to teach you about this, trying to take shortcuts. Shortcuts can be nice, but not when I'm trying to have you learn something, okay? So I had asked you to find the density of water. And so I had a group, and I understand it. When one person in a group suggests it, then everybody says, that's smart, that's smart. But they said, find the density of water, and they said 1 gram, 1 milliliter, density 1 gram per milliliter. And they thought that was what I wanted them to do. Is that what I wanted you to do? That's not what I wanted to do, because I know you didn't measure it, didn't I? How did I know you didn't measure it? Because my balance goes to hundredths place. It goes to hundredths of a gram. You couldn't have used the balance. You get that? So I didn't like the idea that some of you were taking some shortcuts. I really wanted you to find out that the density really wasn't going to be 1. It might be 0.998, but in a room this temperature, it probably is not going to be 1. I don't think you should have gotten 1. So anyway, I do have some drawings of a graduated cylinder. I do have some, you have to read the meniscus. I do use words like tear. Remember what the tear is? Okay, so vocab words. I will use the idea of density. Just like you had to find the density, didn't you? So that was pretty easy. I will have you do a water displacement problem. And you'll say, I put this much water in a graduated cylinder, I lowered a rock in there, and it went up to here, and how do I find the density of the rock? That kind of thing there. One of the easier questions are, I have a picture of the vernier calipers, and I'll say, which part, A, B, C, D, E, points to the inside calipers? Which part points to the, you want to do that again? You want to try that again? Ready? What's this part here called, right here? Inside caliper. How about these? Okay, what about this guy way down here? Depth gauge. That's right. What do you call this thing that looks like an L or a 7 on the side? Just the part here. I'll give you a clue. It's a part that does not move. What's this part called? Now that was on my video, and remember that? But what do you call the part of the vernier caliper that does not move? The fixed frame, okay? Now, what's found on the fixed frame is the fixed scale, isn't it? And then you have the movable frame. And what do you find on the movable frame right here? What is it? Yes, also known as the movable scale, right? The vernier scale. And when you're going to read this, if you go back in my video, or you can just look in your handout, really, you take the 0 on the you take the 0 on the vernier scale, the one that moves, and you read straight up onto the fixed scale, don't you? Anyway, and then what do you do? And I don't have my thing with me. And then what you do is you say, hey, it looks like it's going to be about 2.14 centimeters, and that's without doing anything special. I think it's about 2.14. And how do we make sure that that last number is what we think it is? You thought it was 2.15. I thought it was 2.14. And remember that the vernier line that best lines up, and if the fourth vernier line best lines up with the line above it, then that last number really was a 4. Does that make sense? Now remember, the Vernier scale, or Vernier, it does not give you more sig figs. You would have said 2.14 without it, and you would have said 2.15. I didn't get more sig figs. I just made the last number probably more likely you and I get the same number. Get that? Okay, so that's that. That's some of the easier questions is, can you read the Vernier scale? Can you tell me the parts of Vernier scale? Okay, you should eat that up. The big six, I'm going to ask you about that. Let's go with this one more time. And I won't do a whole lot with pressure because we have an entire chapter. We have an entire chapter just dedicated to pressure. You get that? So what I did tell you yesterday was that we know what mass is, we know what volume is, and we know that density is mass divided by volume. That's a ratio, isn't it? So we got to watch out for ratios. And then yesterday, the lesson was something you've never heard of before. Many things that we measure are called scalar quantities. Remember that? That means direction doesn't matter at all. Magnitude simply says, how big am I? 5 grams, 8 grams. 8 grams has a bigger magnitude than 5 grams. So it only has magnitude. But you're about to enter the world, and for the rest of the year, you're going to have times where I'm going to bring you into the world of the vector world. The vector world says when you measure something, it not only has a magnitude, but it also direction is just as important. You cannot identify a force just by the magnitude. It has the direction too, doesn't it? And in the scalar world, 10 grams plus 5 grams will always equal 15 grams. But what is 10 grams plus 5 grams in the vector world? This is where you help me out. What is it? That's right. The smallest it could ever be, if they were going in opposite directions, the smallest it could be would be a 5 Newton force to the left, right? Like this one? And the biggest they could be, if they were going in the same direction, would be 15 newtons, wouldn't it? But believe it or not, if that's 15 and that's 5, then guess what you could get? See? A little bit higher than 5. More, 10, 11, 12, 13, 14. And that's a different world for you, isn't it? And yet, it's okay. Don't be scared of it. Don't be scared of it. People built your cars. They built roads. They built this building with the vector world. And if you don't want to build buildings, if you don't want to fly airplanes, you could probably live the rest of your life and not worry a whole lot about the vector world. You get it? Somebody else is going to do that. Now, if I got on a plane, though, and I ask my pilot, hey, how you doing today? Hey, do you know what vectors are? If they say no, I might get off that plane. There's no way that an airplane pilot would not know about vectors. You know Jonah? Okay, now he has his license, he flies. And today, we're very lucky because we have these electronic things like GPSs. That makes things a lot easier. But what if that thing went out? If somehow his GPS went out, he'd be absolutely lost flying there, wouldn't he? No, because they teach you how to find your way even without electronics. You get that? And what they do is, you would, as long as you have a radio, your instruments tell you your wind velocity. They tell you I'm going 120 miles per hour north. And then I radio to the I just went over some kind of airport. They said the wind velocity is 10 miles an hour west. I'm going this way. The wind's coming this way. See that? What's going to do in my plane? What's this plus that? I won't end up going that way, will I? I'll end up going that way. Now, if Jonah was trying to get to that city that is due north, he can't set his settings due north. He'll miss the city. You get it? So he has to recalculate and aim this way. If he aims this way, he will end up going due north. Now, we'll talk more about that in some other chapters when we get into, but I want you to at least know that there's this world called the vector world. Okay. All right, one more thing. I understand we have different words for force and weight, but isn't weight a force? Weight is a force. Yesterday, I had an object on a table, and it was a 1 kilogram object. And I said, how much does it weigh? Its mass is 1 kilogram. What is its weight? Patty, you know. I mean, you know. 1 kilogram of mass weighs how much on the earth? We use this all year. How much? 10. Yes, yes, yes. Now, that means that the earth is pulling down with a force of 10 newtons. Is that correct? Why isn't the object going down? Say, the table is pushing up with 10 newtons. You see that? That's what I want you to think. From now on, the rest of the year, if I do get in the vector world, I want you to start thinking about this. I told you about a car going down the road. They're going to the right at 30 miles per hour. See that? To the right. But they keep maintaining the same speed. Isaac Newton said that an object that is not accelerating, it's either sitting still or it's not going faster, it's not going slower. If it's going at a constant speed, it has no acceleration on it. There's no net force. I'm sorry. Yeah, no acceleration means no net force. But I know that my car is producing a force to push the car down the road. Why would I not be accelerating? Why did you tell me there's no net force on my car? And you have to start thinking like this. There must be if there's a force going down this way, there has to be a force going in the opposite direction, because what is this plus this? 0. And if you're going down the car 30, 30, 30, 30, 30, there's no net force on you. There must be another force pushing the car this way. Going back to Jonah. Jonah knows that if you fly, here's your airplane. Okay. He knows that the engines are going to produce a force called a thrust. But as he moves through the air, there's going to be something that the air is going to do. It's going to push back on the plane. That's called drag. Have you heard these? And then he's going to say the earth is pulling down on the plane. That's called weight. And if the wings are made correctly, they will produce a thing called lift. Those are the 4 vectors that make that plane stay in the air. So if he's going at a constant speed, I know that his thrust equals the drag. If I know what would happen if he cut his engines, he would get rid of this one, and the only one would be this one. It would slow his plane down. Yes? All right. Anyway, and then hopefully the wings are made the right way so that you can get enough lift to counterbalance the weight of the plane. You get that? Okay. So anyway, we have a whole year to get into the vector world. I'm not here to spend a huge amount of time on that. All right. And this one here, this is another ratio thing, but pressure is not force, it's force per area. You say, the best example I can come up with is if I tell Clayton, I said, Clayton, is it okay if I push on the back with a force of about 1 Newton? He says, okay, 1 Newton is not very much because that's 10 newtons. So go ahead. Well, then I take a really long pin and I stick him in the back. Oh, I only used 1 Newton of force. And I only used a little force, didn't I? But how much area was that force applied to? And what happens to any ratio where the bottom number is incredibly smaller than the top? Ooh. So what did I do? Pressure. See that? It was only 1 Newton of force, but a lot of pressure, wasn't it? One more thing about pressure, because we'll leave this up. I have a knife, and here's my knife, and I haven't sharpened it for a long time. I put a force on it, and I'm trying to cut the tomato, and I say, this is not working real. I sharpen the knife. I put the same amount of force in there. See the area here? How much pressure can I put here? This much. How about here? See? When I make the areas, whoa. That's why a sharp knife works better. A knife is really works on what? What word? Not just force, but what? Pressure. Huh, that's interesting. Hey, I live up in Canada. We had a lot of snow. I think I'll go walk in the snow. Oh no, my foot goes down. My foot goes down. I'll never get to the store by walking. I guess I weigh too much. I think I'll put on some snowshoes. That'll make me weigh more. And I walk on top of the snow. What happened there? I weigh more, but what happened to that force? I spread it out over more area, less pressure. It was pressure that was making me crush into the snow. Isn't that right?
Wow.
Pretty neat ratios, right? All right, and the last one, we started this yesterday. This is the one we did yesterday. I was really proud of you. I tell you what I really like about this class. You are willing to tell me what you think, even though it may not be correct. You're willing to say, this is what I think. And that's important. That's how you learn. So I asked you a question yesterday. If you take a feather and a bowling ball in a vacuum and you drop them at the same time, why do they hit the ground at the same time? I'm going to show you a real quick example of that, okay? If you had a feather and it only had a mass of about 0.001 kilograms, it would only weigh about 0.01 newtons. And so how much would the earth be pulling on a 0.01 newton feather? 0.01 newtons. Okay. How about a bowling ball? How much does the earth pull on a bowling ball?
60.
A lot, isn't it?
Yeah.
So even though I know what you want to say they hit the ground at the same time because the earth pulls on all objects the same in a vacuum. That is not true. We call a bowling ball heavy because the earth pulls on it more. You get it? So the earth will always pull on heavy things more than light things. So that's not the reason they hit the ground at the same time. You say, yeah, but that's what I always thought. You know why? That was easy. And sometimes we take the easy route, don't we? Let's tell you how it really works. How does it really work? Isaac Newton had this thing called Newton's second law of motion, okay? I already talked about that before, haven't I? He said, if that's zero, I don't care what mass you have, if that's zero, that's got to be zero. The net force has to be zero, doesn't it? Now I want to take the same equation, and I'm going to rearrange it a little bit, and it's going to look like this. A equals, let's divide both sides by m. And here's what Newton said. What is the cause of acceleration? It's not the force on you. It's the force per mass. What do you think? Let's go down here. Ready? What is the force of this object? 0.01 newtons. And that's its weight, right? That's the force on it. So acceleration equals force per mass, 0.01 newtons. That's the force on it. What's the mass? 0.001 kilogram. And what you end up getting is a number very close to 10. And you don't know this yet, but a newton is a kilogram meter per second squared. You don't know that. Kilogram meter per second squared divided by kilogram. That gives you meters per second squared. Now we go over here, and we do the same thing over here. We had the force on the object was 60 newtons, and the mass was 6 kilograms, and that ends up getting 10. What happened here? What is the force on this object? Huge. What is the force on this object? Little. So here's the way I think conceptually. Ready? What's the force on this object? Little. What is the mass of that object? Little. And what do you end up getting? What is the ratio of force to mass? About 10. What about this guy? Boom. What's the force on this object? Huge. What's the mass of the object? Huge. What do you end up getting? Oh. Do you understand what I'm talking about? The world of ratios is something that physicists use all the time, okay? And some of the best stuff in physics is in the world of ratios. So you can see why I'm already introducing you to things like Mr. Short and Mr. Tall. And we actually already did another one. Here's another one we already did. You already did a graph that looked like this. Mass, volume. Remember that? Now watch. What's happening during this experiment? The volume is getting bigger and bigger and bigger. What's happening to the mass? It's getting bigger and bigger and bigger. Is there anything that's not getting bigger and bigger? Yes. The slope right there is the same as the slope right there. See? How many slopes does a straight line have? 1. Why? Because let's imagine this number is 20 and this is 2. Okay? And then this is 40 and this is 4. And this is 60. See? The volume gets bigger. The mass gets bigger. What doesn't get bigger? Starts with R. The ratio, in this case, the ratio is the slope as it was on the y-axis divided by x, right? And what's 20 over 2? What's 40 over 4? What's 60 over 6? Whoa. And so if I were to take any object you can think of, and put it in a vacuum, and I said, how much do you weigh? That's the force on you. And how much mass do you have? What kind of graph would I get? Help me out. What kind of graph would I get? Does mass stay the same? Mm-mm. Does force stay the same? Mm-mm. Anything stay the same? The slope. What's the slope? What's the slope of this line? Isn't that right? Isn't F over M? And on the Earth, that number there is a constant. It's called Earth's gravitational constant. Now, be careful. You're going to hear all kinds of people say that Earth's gravitational constant is the pull. The pull of the Earth on all objects is the same. That's wrong. It's wrong. Do you notice the units? What are the units for pulls? What are the units for pushes and pulls? Oh, man. That hurts. What is it? I know. What's the units? Newtons. The Earth's gravitational constant can't be the pull of anything. It would be in newtons, wouldn't it? Earth's gravitational constant says that the ratio of how much you're being pulled on per mass on all objects is the same. That's what's the same. You understand that? Now, we have another chapter on that. We'll get to it again, but I just want you to understand that this world of ratios is big. You don't like to get in that world of ratios a lot of times. You want to stay away from it. Remember the Mr. Short and Mr. Tall? Many people, they want to stay in that world. He was 2 buttons taller, so it'll be 2 paper clips taller. And we can't do that. We would have never built buildings or airplanes or cars or even cell phones. That would never happen if we didn't enter the world of ratios. Yes?
So is 10 meters per second squared also 1 g?
Yes.
Okay.
And even though later I'll teach you it's really 9.8, if we do calculations, we'll use 9.8. I didn't want to get into all the fancy little numbers here, okay? And 1g means you'll accelerate as if you were on the planet Earth and you're being accelerated the same way all objects are. Now again, this is in a vacuum, but even if I went to another planet, they would have a different gravitational constant. Get that? On the moon, it's less. And so when you drop an object, it doesn't accelerate as fast, does it? It falls slower, doesn't it? When you jump up, you don't come down as fast. You don't accelerate back down as fast. And that's why it looks funny when they walk on the moon. Seems like it took longer to get up on the step, and it took longer to come down from your step. All right, is this opening up your mind a little bit? That's one of my main goals for you taking physics, is that you kind of think differently. I hope I can get you to think a little bit differently, all right? All right, let's go to the next part. So we'll do a little bit more with the ratios today, and I do have 2 leftover questions. I want to mention that to you, full disclosure. I do have a couple questions about Project MLK, and because you did that project, and so I'll tell you what they sound like. Okay, here's what they sound like. A person did a liter and got 920 milliliters, and what is their percent error? Now, you did that project. You were supposed to calculate your own percent error. So how do we do that? What is the percent error for that student? I only have two. Those are called leftover questions from before. You know how to do percent error? Remember that? Okay, so what are you going to do? 920. That's the experimental value. What was your standard? What should you have gotten? Okay, there we go. You're sounding great. I'm telling you. So far today, you're sounding good. And then what do you divide by? And then what do you multiply by? That's it. What's that person's what is that group's percent error? 8. You're right. 8% error. And the next question I might ask is this one. They did the liter twice. And the second time they got that. What grade? What was their final percent error based on the project rules?
4%.
Ooh, how'd you get that?
2% error on the second one. And then
Man, I like that. So you quickly figured out that was 2%. Ooh, I like Jeff. Good job. 2% on this one, 8% on the other one. Since the second was better, you take the average, right? Average would be what? What's the average of 2 and 8?
oh wait.
But I liked how you're thinking. What's the average of 2 and 8? Okay, so I would give them a 5% error. How about that? But I like how you jumped on that, and even though you said 4, I think you just were thinking.
I'll just think of simple division.
Yeah.
All right. Now what I'm going to do is spend the rest of the time on some of the stuff that you did reading a little bit. We know that density is mass over volume. Is that correct? And it's a ratio. And so we have to be a little careful in our thinking. I'll get these two objects again. All right, both these objects. What can you see? What can you see? You see volume. Now, if you can't see mass, and density is mass divided by volume, then you cannot see density. Now, when we pick things up, we kind of think there's something unusual about this, isn't it? There's something unusual, and we say, that's heavy. And I always tell people, so's a ton of feathers. Would you rather put this on your head or a ton of feathers? And you're saying to yourself, what? Can I tell you something? A ton of anything would crush your head, okay? Oh, so when you say it's heavy, what do you really mean? What's that mean? Heavy for what? Its size, right? It's heavy for its size, isn't that right? Anyway, so be careful about that because density is heavy for its size. It's like how much mass can you pack in a little space like that? Let's take a look over here. I'll tell you what I don't like. I like the author of this book. I would not have used the idea of bread because bread has one name. But what's bread made of? It's got starch stuff in there, doesn't it? Guess what's in there, though? It starts with an A. Air. I don't think you should have done that because if you're going to do the bread, you might as well just take a balloon, okay? Let's do a balloon. Ready? The balloon, the air in the balloon has a certain density, right? What if I do this? Let's take a look at, think about ratios. Mass over volume is density. We're going to think conceptually. Ready? What if you take and squeeze a balloon full of air? What have you done to the mass of that air? I'm looking at your faces. If I take a balloon full of air and I squeeze it, what did I do to the mass? Nothing. Did I add any clay? Remember that? Did I add any air? Did I take any air away? So I'm going to draw the M the same size. What did I do to the volume? What happens to any ratio where you keep the top number the same and the bottom number gets smaller. Isn't that what's going to happen? Let's say you don't. How do you know that? I'll play a game. Let's play a game. 10, 2. What's 10 divided by 2? 5. All right, keep that 10 and make that a lot smaller. All right, how about 0.2? Whoa, see? What happens to the ratio? It becomes 50, doesn't it? By the way, that's a bad number because that's something I ask on the quiz tomorrow. When you do eventually, and I am going to switch density detector around only because they're changing the exam, but I will have you do a density detector. It's too memorable not to do it, but I may have to do it after the exam. I may have to do it in January. So when you have a team and you do a density detector, and somebody says, I figured out the density of this object, it was 50. You had to sit there and say, do it again. Do it again, because the most dense thing on the planet is what? Only 22. Don't tell me the density is 50. You get it? And then you're a good partner, aren't you? You're a good partner because you remember this. And here's what I want you to know about this chart. As far as I'm concerned, in this chart, we have a group of the absolutely super dense material. The chance of you running across very much of this is not great. I don't think you're going to run into osmium. It's possible. Let me know if in your lifetime if you ever run across a kilogram of osmium. And so osmium is up there in iridium. Osmium and iridium should be up there too, but iridium and osmium, it's interesting that, and platinum and gold. Look at those four right there. See? OS, IR, PT, AU. Those are all kind of the same place, aren't they? So the super dense materials are up in here. Another one would be uranium. Actually, some of the new elements they're discovering, some of them are very, very dense also. But sometimes you only have like 1/100 of a gram of something, and they actually decay into another element very quickly, so you're probably not going to run across that either. So in your lifetime, you might run across some gold, but I wouldn't think it'd be very much. I wouldn't think very much, because the gold is really way up there, expensive, isn't it? Now it is. Yeah, if I had like 30 years ago, if I could knew the future, you could buy gold pretty cheap, sort of cheap. And then you could have made, your money could have been multiplied by 50 times. That's how people make money, if you guess right. Okay, so the super dense materials, make sure you know those. Now, let's go to the things that you think are dense. Lead. I actually think this does feel kind of weird for its size. Lead is only about 11. I shouldn't say only. Lead, in your lifetime, you ever run across lead? How many, any go fishing in the ocean, you know, those great big weights, those are, most of those are lead. Car batteries, you know what metal is in car batteries? Lead. That's why a car battery doesn't take up much space, but it seems pretty heavy for its volume, doesn't it? It's got lead in it. Okay, silver, a little bit less than lead, and then you will run across some copper. I believe you will run across copper, and that's around 9, something like 8 or 9, between 8 and 9. Now, iron and steel is mostly iron, so I'd say things that are dense around 8. So here are things you'll run across here, and I want to say that then what you end up having is, I'd say most rocks. Most rocks are probably around between 2 and 5 in density, but every once in a while you'll get a rock that has metal in it. You'll get a rock that has a metal in it, and it'll be dense. It'll be pretty dense. But most rocks might be like somewhere between 2, 3, 4, 5, something like that. And the next thing I'd like you to know is, here's aluminum. That's we call it light, but we really mean not dense, right? And the next thing is, look at water. Where is water? On purpose, they made the density of water 1 gram per cubic centimeter. Because if I had a liter of water, and I had a liter, this was on the last test, wasn't it? I think I'll ask it again. If I had a liter of water, it weighs how much? 1 kilogram. You did a project on that. So what if I gave you 1 liter of lead? How much would 1 liter of lead weigh? Well, by them being smart enough to make the density of water 1, all right, then what?
That would be 11.2.
If that's 1 kilogram, does that make sense to you? Because lead can pack 11.3 times more mass than you can, Walter, in the same amount of space. Oh yeah? I can pack a kilogram in that space. Well, I can pack 11.3 kilograms in that space. See how we're doing that? A little conceptual thinking there? All right. It is true that they found out later that water is one of these unique things. We'll have another chapter talk about water, but water, like everybody else, it gets a little more dense as you cool it. Steel, water, everything gets a little bit more dense, not much, a little bit more dense as you cool it. And then water does this weird thing. When it gets to 4 degrees Celsius, it's about 39 Fahrenheit, it starts doing something where the particles start moving away from each other. And between 4 Celsius and 0, before it freezes, it actually gets a little less dense. And it's one of the very few materials on the planet that a solid actually floats in its own liquid. I promise you, solid gold, if you put it in liquid gold, bloop, it'll go down. Solid gasoline in liquid gasoline, bloop, it'll go down. It's more dense. But ice, what did I say? Ice. And that's why you see ice has a density of what? Interesting. Ice is a little less dense than the water that formed it, isn't it? Okay. Anyway, a lot of you think that the oceans are really salty. They are. But how much does all that salt add to the density? If somebody went to the beach this weekend and you wanted to say, I'm going to do that. I'm going to bring it home and I'm going to find the density of salt water. And you could do that, couldn't you? Find the mass, find the volume, find the density, and what would it be? What? I thought it was going to be like really big. No, it's just a little bit more than 1. I will say if you happen to go to Utah, Great Salt Lake, it will be more dense than that. And if you go to the Dead Sea, it'll be even more dense than that. And so, anyway, we have a whole other chapter on water and density and stuff like that. That's not what I'm here to do there. Excuse me. Is there anything in the reading that bothered you? You read it and you said, I don't know about that. You might want to reread some of this and say, well, now I think I got these straight. This big 6 stuff. Here's one. Here'd be a good question for a quiz. Finding volume by water displacement. Ready? A completely submerged object displaces a blank of water equal to the object's own blank. When you put water in a gradually cylinder and you put that rock in there real slowly and the water level goes up, why are you doing that? If it starts at 30 milliliters and it goes up to 38 milliliters, why? What made it go up? There's a rock. If I start with 30 milliliters of water, I put the rock in, it goes to 38. What does that tell me? Do I have 38 milliliters of water? No, I only have 30. And so guess what? A completely submerged object displaces a what? A volume of water equal to the rock's own what? Volume. It's volume that displaces water, right? It's not mass. It's not weight. It's volume. Anyway, that's what this drawing here is talking about. And we won't do buoyancy. We won't do Archimedes' principle because that's another chapter. Everybody get that? So I won't ask you that. I won't ask you Archimedes' principle. How about that? Oh, here's what I was looking for. Okay. Let's practice this. First of all, I have the fixed scale, and here's the movable scale, also known as the vernier scale, right? Now, they don't write the number 0 there, but there it is. The 0 on the vernier scale, you always read straight up from that line, don't you? Now let's pretend I don't have the vernier scale, but I'm just trying to read it. I'd say 5.2, I don't know, it's getting up there. I wouldn't say 9, but 8, maybe 8, 7. I don't know. What do you think about that? Is that what you say? Now, you might read it and say, no, I think it's 5.29. And somebody said, no, I think it's 5.27. All right, so the French mathematician, what he did is he took a centimeter and he took 90% of the distance and divided that into 10 pieces. And that's how he made this. And somehow it works. And here it has, go ready? Which vernier line lines up the best with a line above it? No. Oh, no. And by the way, I knew I was going to look at the end of it, right? Oh, look. Yeah, there it is. Look, it's which one is it? The not the 5th, not the 6th, not the 7th, not the 8th, but the 9th vernier line. That tells you the last number has to be the 9. You get that? What do you think? Okay. Now, the last thing, I want you to do well. It's actually a mini test. It's not a, it's a quiz. I mean, let's do a little, let's play a little game, okay? I got a little time here. Let's have a party. And we're going to do, you want to have a party, and you said, I just want to have a party that's so variable, all right? But you sent out the invitations, and it's to 10 boys, but it says, if you want to come to my party, each boy must bring 3 girls with him. Now, the guys are saying, oh, yeah, I'm going to that party. The girls say, oh, no, there's going to be a lot of girls, not as many. I don't know. But anyway, let's pretend that's what happens. And the party's supposed to start at 7, and only a couple people got there at 7. You want to be fashionably late. Is that what you want to do? I don't know about that. So there are 2 boys and 6 girls, or 8 people. Okay. And then at 7:30, there were 6 boys, 18 girls, 24. And so if I had to make a graph of that, it would look like this. It goes, how about boys? Boys went like this. It went from 2, 6, 9, 10. Okay. That's what happened to the number of boys at that party. What happened to the number of girls? This is boys. What happened to the number of girls? What happened to the number of people? Now, let's think about this. All night, the number of boys changed, the number of girls changed, the number of people changed. Is that correct? If you had to say, that is the pattern. It was changing the whole night. Let me ask you this now. Sketch this graph here. Number of girls, number of boys. What would that look like? What would the girl to boy ratio be at 7 o'clock? What is the girl to boy ratio at 7 o'clock? Girl to boy? That's 6 over 2. 6 over 2 is 3. What's the girl to boy ratio at 7:30? That's 18 over 6. Oh, that's 3. That's 3. That's 3. That's 3. Oh, what? What happened? The number of boys and girls changed all night. Is there something that didn't change? The ratio. Oops. Just turn it off, okay? Yeah, just turn it off. So, what would end up happening is, you'd end up having something like this, wouldn't you? And what's the slope of that line going to be? 3, right? Because it's y over x, and the ratio of girls to boys the whole night was 3 over 1, wasn't it? Okay, go ahead and see if you can fill this out. What about this one? Total people to boys. 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 Do. Oh. I was trying to make a party that was not constant. I wanted to change all night. What if you did the next one? Boys to girls. Boys to girls. 0.33, 0.33, 0.33, 0.33, 0.33. Everybody see that? What if you did total people to girls? Total boys to total people. What are you going to find out? There were 3 columns that changed all night, didn't they? But there's at least, in this case, there's 1, 2, 3, 4, 5, 6. There are 6 things that never changed at all during the whole party. And they were ratios, weren't they? Does that make sense, my dear? It's kind of a weird party, but that's a lesson you can learn. Anyway, I just kind of sketched that on a piece of paper. I just thought, if you thought about this, yeah, you're right. The ratio of boys to girls did not change at all the whole night. Okay. We already had a quiz on that. So that's I took those out. I think that's about it. That's about it for me. Let me think. Is there anything on? Oh, I know. You did a lab last week, didn't you? Let's talk about this. Let's say I draw one of these, okay? And what if I give you the mass? And what if I give you the mass and I give you this? And I give you this. How would I find the density? Okay, so density equals mass over volume. So how do you find the mass? I'm going to tell you that one, okay? How do you find the volume? How do you find the volume? You did a lab, you had to do it twice. No, more than that, maybe. Well, you have, can I show you how to memorize this? How do you memorize the volume of a cylinder? Okay? Think about the top. What's the area of that circle? What's the area of any circle? Isn't that right? So watch. Pi r squared times what? See? Here's a circle. Many circles. Anyway, if you do that, if it's pi r squared times h, you can get that. Now let's get the units. Here's where you gotta be careful. The vernier calipers would probably give you the diameter, wouldn't it? The diameter, let's make one up. Let's say the diameter is 4 centimeters, right? What's the radius? Okay, and then I have to plug that in here, don't I? But what's 2 centimeters squared? 4 what? Centimeters squared. Another thing is, and the height is going to be, let's say it's 10 centimeters here. What's pi times 4 centimeters squared times 10 centimeters? That would give me 40 pi. And what's a centimeter squared times a centimeter? And I'll put that in the calculator. But the units come out right, don't they? What is a cubic centimeter? What's volume, isn't it? I must have done it right. One more. Ball. What is the one for a ball? Cubed. And you know why? Because you better cube that, because that's the only thing that has a label on it, isn't it? See, it's gonna be cubic centimeters. All right. I think that's all. That's pretty much all. That's what's on there. Yes.
Do you need to memorize the formulas for like sphere and cylinder for the test?
Well, yes. Okay. and the density equation. How about that? I'm trying to think if there's anything else, any other equation you have to memorize. And again, I think you can do pretty well. Make sure you have a calculator tomorrow. There are going to be parts of it where I'll say you must use sig fig rules. You get that? So don't forget to remind yourself about some sig fig rules. Well, I hope you have a nice day today. It's supposed to be pretty nice out. You got to have the ACT postponed to next week. That was pretty nice. So, all right, thank you very much.